Good afternoon. So the next mini course about totally geodesic subspaces of hyperbolic manifolds was going to be given by Michelle Ichoux, but unfortunately she fell ill and did not manage to arrive. So we decided to make a substitution, and this mini course will be given by Matthew Stover, Plinio Muriliuk, who is not here today, but he will be tomorrow, and myself. And we decide how to split the lectures. So the topic will be the same, but contents probably will be different. So this very
relative quality TBD. But we decided to do this last night, so be generous. Okay. So yeah, thank you all for coming. I must apologize for not being Michelle, but I'll do the best I can. So yeah, in fact, going back to the morning lecture, a lot of what we know about negative curvature, the sort of base input always comes from a hyperbolic manifold, okay? Usually a compact hyperbolic manifold. So just to keep things short, so I'll say, so mostly what we're interested in, let's see. Hyperbolic manifolds. Of finite volume. And so what this is going to mean is that M admits a metric, a complete metric, of constant curvature -1 and finite volume, okay? And so maybe the basic question without which any of the examples from the previous lecture would exist, so do such manifolds exist, okay? And so the first topic is going to be to produce a construction that says yes. And there's a sense in which all of our knowledge of compact negatively curved manifolds comes from this invariance and then topological tricks. And it's a sort of interesting open problem whether you could ever get started without this. I think coming up with a completely new construction of negatively curved manifolds that totally is ignorant of this, well, one, you'd be sort of crushing my entire life because this is what I do, but it would be sort of interesting. Okay. So models of hyperbolic space from quadratic forms. All right, so Hn, what is this? This is the unique, simply connected manifold of constant curvature. -1, okay? And just to save me chalk and save IMPA some money, this would be complete. Everything would be a complete metric of constant curvature. This one's not finite volume, but so I'll always say finite volume when I mean it. But in particular, it's a sort of classical fact that if you have a compact manifold, then completeness comes for free. There's also geodesic completeness, which is equivalent, but anyways, we're not going to get into that. And the point is that There's a standard hyperboloid model, which perhaps you've seen before. If you haven't, that's fine. It's coming. But you don't have to use the standard quadratic form, and that variation is going to actually allow the space for us to build many, many different examples. Okay? So we're going to start with the quadratic form. Q of x equals on R m plus 1. Okay. We can think about this as coming from an inner product. Transpose for Q, the matrix. With the -1 in the first slot and the 0th slot, and then 1's all the way down. Okay, so and I'm going to sort of mesh the matrix with the form. So Q of x is just Q of x here. Okay. But the fact is, and this will be useful, so suppose that Q1 is a symmetric matrix. Symmetric real matrix. Okay. Then the first fact is that it has real eigenvalues. This is one of these facts that you learn in a course in linear algebra, sometimes without much motivation. You're like, oh, we're going to study symmetric matrices. Oh, they have real eigenvalues. And then you sort of move on, and you're like, why do I care? You know, if maybe you're just reaching that point in your life where now you care, but I hope not. And there is a basis where it is diagonal, okay? Right, so that just means you can diagonalize it over the real. So it has real eigenvalues, and you can also find a change of basis so that it's diagonal. So there exists a change of basis matrix A so that transpose A Q1A looks like lambda 0, sorry, up to lambda n. Okay, and just in case this weirds you out, I'm sorry, but you'll have to get over it. I write my transpose on the left-hand side because I have to take transpose inverse all the time. And so in my life, this is a necessity. Okay? If you don't like it, you know, there's a beautiful coffee room with monkeys outside the window. You'll have a better time. Okay. So we can talk about, and so you can again sort of scale your basis. You could again, now you could scale basis so that your form is a sum so I equals 0 to k of I'm going to do k minus 1 so I don't screw up elementary mathematics squared. Sum I equals k to n xi squared, okay? So, right, this is saying that we've done a change of basis so that when I pair the first basis element with itself, I get lambda 0 all the way up to lambda n. And so we say that Q1 has signature n minus k, comma k. Okay. So our original quadratic form, so the original one, our Q, has signature n comma 1. Right? We have 1 minus and n pluses. All right. And so now given this Q1, I got k of them here that are minuses, and that means I have n minus k plus 1 pluses. Is that, yeah? Yeah. Okay, and so by equivalent, I just mean the above process of change of basis. Okay, so this may all seem a little bit pedantic, modulo my ability to count, which is clearly not so pedantic. But being able to understand this variation, in fact, the change of basis that does it is going to be fundamental once we get to the hard math, once the number fields get involved. So all right. So now let's take any Q. Signature n1, then we get a hyperboloid. H, which is going to be the set of x. Rn plus 1, such that, so I'm just going to take the upper sheet, and q of x is minus 1. Okay? And what you should be thinking in analogy here is you have that the sphere is the set of the sum xi squared equals 1, okay? But now we're getting a hyperboloid instead. And just like with the sphere, so you can describe the tangent space to a point of the sphere in terms of the set of vectors such that v dot p is 0, you can do a similar thing here. So if we have a point x on our hyperboloid, we can describe the tangent space to x of our hyperboloid as being the set of vectors v such that I just q1 of x v equals 0. Okay? In fact, we can give a metric by taking the restriction of Q1 to this tangent space. Okay, so this gives us a Riemannian metric. And that's exactly, in the Euclidean case, what are we doing? Well, the sum of the squares, this is the Euclidean length on Rn plus 1, and we're restricting that to the sphere, and so you just restrict the regular dot product to this space. That gives you the spherical metric on the sphere. You do the exact same thing here, now just using this new quadratic form, right? Because the sphere is defined as the level set of 1. For the standard quadratic form, the dot product on Rn. And so out of this process, you get the Riemannian metric on the sphere. You do the exact same thing by this restriction. Okay? Okay. And one could, let's not and say we did, you can compute that this has constant negative curvature. But the real upshot here is that geometric invariance can often be reduced to linear algebra. Okay, and this is great for me because I really peaked at linear algebra, and then once things started getting nonlinear, I started getting worse and worse, and so I've sort of made a career out of just doing linear algebra and studying hyperbolic manifolds, and my advertisement for this course is you can too. Okay. So let's maybe talk about the isometries of this metric. So given a linear map, preserving this matrix Q1, so transpose G, Q1G is Q1. Right, and so the first exercise, if you haven't worked through this once in your life, you should do it once and then never again, which is why I'm not going to. Because I promise. So if you have something that preserves this quadratic form, then it will take things of norm 1 to things of norm 1. But also, it will preserve the inner product. And you have to use the fact that the determinant of the linear map is that linear map again. So there's a little bit you have to do, but this is something you can check. So what we get is a map from ON1, get a homomorphism. ON1 is a set of G and GLN plus 1R, such that transpose G preserves this form as a matrix. This is just saying under change of basis, you get the same symmetric matrix back. The isometries of Hn, but you have to be a little bit careful. I'm going to put a little circle there. And that circle just means that you need to preserve the upper half sheet. Right. This hyperboloid has another sheet that's down there, and we don't want to go down below the board. We want to stay above. So we get a homomorphism, but you have to be careful of that caveat. Okay. In fact, so this is everything. And here's maybe a sketch of this. If you've never seen this argument before, this is the argument if you want to prove that a certain group is an isometry group. So you prove O1 is transitive on points. Okay. And then prove that the stabilizer of X acts transitively on its tangent space on, let's say, unit vectors. And so this is telling you that it acts robustly, simply transitively. And it tells you roughly that you get everything. Let's see, do I want to go into this calculation? No, maybe not. So let's, to make our lives easier, let's return to the standard form. Actually, no, I want to use, let's use I want to use this quadratic form for a particular reason that I'll explain in a second. But so the matrix, yeah, this is fine. So the matrix is going to be 0, 1, 1, 0. There's a giant identity in the center. Okay. Prove that Q0 is equivalent to the standard form. And so the nice thing about this is you can find some nice vectors. So maybe I'll pause for a second since I've been just blowing through this, all of this. So can somebody give me a simple vector of norm -1 for this form? And then last one. Yeah, exactly. All right. So this lives in the hyperboloid for this model. We call this H0. Okay. Well, you need to prove that something that acts as the identity on a point, acts as the identity on the neighborhood of a point, and then acts identity everywhere. That's the last step.
Yeah, but even if it just gets, you need to show stabilizers are like O(n), right?
Uh-huh.
But
Yeah, yeah.
It's not enough to say that, right?
But it follows. I'll add it as a, yeah. But like I was saying out loud, there's even another step that you need that I'm really sweeping under the rug, which is if you fix a point and fix its tangent space, then you actually act trivially on a neighborhood of that point. And that's a subtlety that that's a place I don't want to go. But it's necessary. It's actually necessary to prove that. That's a fact from, it's a standard fact in Lie groups. But yeah, so what you can check now is that the matrix, I'll call it AT, which is e to the t over 2, big giant identity, e to the minus t over 2, preserves this form Q0. Okay. So t is just any, I'll take t to be positive, doesn't matter. I'll take inverses, I'll take all of R. What the heck? I'll take the whole subgroup. Okay, so this is a one parameter subgroup. If you multiply them, it's just additive in T. And so what we can get then is that A T times this 1, 0, minus 1, which is just T over 2, zeros, minus T over 2. So it lives in here, right? So this gives us a path, sigma from R to this hyperboloid. And so next exercise is that the image sigma is a geodesic. In H0. And here's how I want you to prove this, if you haven't before. An involution tau in okay, now this is going to be of the spirit of things that I think Misha is going to get into starting in the next lecture, given what our plan is now. And so what's the reason for this? Okay, so it's going to be relevant later to think this way, but the key point is that fixed sets of isometries are totally geodesic. So, okay, one could write down the metric in coordinates and then write down, the integral of some path and then minimize over integrals of paths and show that it minimizes, but please, please, please don't do that. I mean, if you really want to, go ahead. But the point is that really, if you want to exploit the linear algebra to understand locally symmetric manifolds in general, you want to use trickery like this. You actually want to show things are fixed points of involutions, because then you don't have to go and do some calculus. And especially if you continue studying more general locally symmetric spaces, which would warm my heart, the curvature is no longer constant, and these integrals become very difficult if you want to actually compute the distance between 2 points. And they're very simple locally symmetric spaces where we don't even know the convex hull of 3 points. And so this is how you exploit symmetry to avoid hard calculations. This one isn't so hard, but I would certainly never do it in public. Okay. I think that was all I wanted to say there. All right. So we have our hyperboloid H0. And so if we look at these points, so maybe here is my original base point. And then we have, so we'll call this x0. And we look at the orbit of this, that gives us one geodesic, which you can notice that this is the intersection of the hyperboloid with a linear subspace. Okay? And my goal now is to explain that what totally geodesic subspaces of Hn look like. All right. So we have Rn plus 1, and we have our hyperboloid living inside. But you can take any hyperboloid for any quadratic form. Take the standard one again if you want. It's fine. And so what we can do is we can start intersecting subspaces of Rn plus 1 with our hyperboloid. Okay. And we can ask, what is the geometry? So to start, so maybe we'll have W living inside Rn plus 1. we can consider the restriction of your quadratic form to W. And so things could go a little bad. You have to be a little careful, and now this is but let's assume, so maybe I'll call this Q sub W. So there could be something bad, but let's just assume that this restriction has signature k, comma 1. Okay. Well then, what you see is that the subspace W intersect the hyperplane is a model hyperbolic k-space for this restriction. Right. And so that gives you a map, at least. So you get an embedding and the point is, this is totally geodesic. Meaning that the geodesic in Hn between any 2 points is contained entirely in the image. Okay, so in Riemannian geometry, you have to define this locally, but here it's just a total global statement. Okay, I don't want to get too much into this because I want to get into the actual math. But so one thing that we're going to sort of flush out over time is this. So this is a little bit fast, but I'm just sort of laying it out, and eventually, as we start generating examples of hyperbolic manifolds, we'll start to fill in the details of this and see that this becomes a very rich theory, especially once you throw a number field into the mix. Okay? So I'm sort of charged with laying out a bunch of stuff, and then I'm going to leave it to Misha to clean up the mess. Okay. So like I said, we're going to be looking more closely at all of this as the course goes on. And let's see. Yeah, so I'm going to do one more little thing, and then we're going to take a little break. So a bit of number theory. So in the second half, we're going to look at a construction. And it's going to come from a little bit of number theory. And like I said, it'll start to come back to these topics. So K is going to be a number field. So finite extension of the rationals. All right, and so by the primitive element theorem, don't worry, the number theory won't be too bad. This is I think, the deepest fact. I'm going to state 2 theorems. We can write K as being Q adjoint alpha, where alpha is the root of some irreducible polynomial P in Q adjoin T. All right? So this polynomial P, we can really think about this as, so alpha has embeddings into R or C, right? This is just picking the various roots of the polynomial. So, so we're going to call these embeddings. That's by roots of P. So alpha is just a symbolic root, and we're going to pick all the roots. So we get a map, an embedding of K and a product of the reals and the complex numbers. And the caveat here for the theorems in number theory, I'm going to cite, maybe green's not so good. We're going to take one factor for each conjugate pair of roots. Okay? We'll see why in a second. But so I get an embedding here just by taking all of these. All right. And so we'll, here, O sub k will be, set of x and k such that the minimal polynomial, so it satisfies a monic z polynomial, the ring of integers. Maybe I'll give this embedding a name, capital Phi. So the theorem is that capital Phi O sub k is discrete in this product. Okay. So just some examples here, and then we'll take a break. Yeah, so this k has a minimal polynomial from the primitive element theorem. And then I can pick the roots of that polynomial. And then I just take linear combinations of that root, and that gives me an embedding of k. Right? So here I'm thinking about alpha as an abstract root. It's not a complex number. It's just an abstract solution to this. And then by picking a root of the polynomial, I can extend to get a map from this field into the real numbers or into the complex numbers. And let me, hopefully this will clarify. So you think about alpha as being a root of, did I use x? Equals 0, and I can send alpha to square root of 2, or I can send it to minus square root of 2. And so I can take a plus b alpha, I can map it to a plus b root 2, a minus b root 2, living in R2, and then z adjoin root 2 becomes discrete. In there. Okay? That's a 2. Okay. So you can try to think about why z adjoint root 2 is not discrete in R. And then the other example to motivate why we only take one factor in the complex case okay. And so for the complex numbers, for z adjoint I, you only need to take one factor of c. You don't need to take both roots of x squared plus 1. Okay. So what's going to be our goal after the break, which will be a wonderful break, is to use this to build discrete groups acting on the hyperbolic plane. Okay. So we want to get fundamental groups. So what does a fundamental group do? A fundamental group acts discretely and freely with quotient your manifold. Right? So our goal is going to be to use this fact and then some of this quadratic form nonsense, which I hope to slowly drag you on board that it's all going to be OK. And we're going to build some discrete groups acting on hyperbolic space. All right? But I definitely owe you a good solid 5 minutes plus epsilon. So let's do that. OK? I take the dead silence. It's time to go. OK. I'm as ready as I'm going to be, which we can all judge over coffee afterwards what that is. OK, so what am I going to try to do? So I just started yapping about using different quadratic forms to build models of hyperbolic space. And somehow you can do some linear algebra to get some geometric invariance, and we're going to get into the guts of that more later. But what I'd like to do is convince you that this fundamental fact from number theory is useful to, combined with that previous idea, produce discrete groups acting on hyperbolic space. Okay? So our goal is to use the fact that to produce discrete groups. Acting on hyperbolic space using models from different quadratic forms. All right. All right, so we have an induced embedding of matrices. I'll put an n plus 1. So actually, I'm just going to say, let's put it this way. All right, so recall here that R is the number of real roots of the min poly of K, and this S is the number of complex conjugate pairs of roots of the minimal polynomial, okay? This is also discrete. All right, so let's think that through for a second. Well, the induced topology on matrices just comes from thinking about it as, r to the n squared, okay? And so the induced topology from this embedding is going to also have this discrete, because it's discrete in each entry, and so it's discrete in the product, okay? So there's a discrete group. All right. So out of a number field, I have produced a discrete group. Oh, these should all be n plus 1s, sorry. Okay. So out of number theory, I've produced a discrete group of matrices. Now this doesn't do what I want it to, so our point is going to be to have a lemma that will let us act on a hyperbolic space. All right. So here is, I believe, on number 4. So we're going to take a product. So we have a group G, capital G. It's a product of two groups, G naught and G and K, with K compact. Let's let and pi from G to the first factor, G naught, be projection. Gamma in G is discrete, prove that pi of gamma is discrete. In G naught. Okay? In a certain very particular sense, this is the motivation for the arithmetic construction. This is the tool that allows you to build many, many, many discrete groups out of number fields. Okay? So we have a discrete group of matrices. Oh, we take maybe GLN to get a group. We have a discrete ring of matrices here. And then we're going to use this lemma. Now, these are all non-compact, so we're going to have to be clever. But fortunately, we're all clever, so we'll be okay. But so, if understanding this is really understanding why one would start to even try to build the arithmetic machine from this point of view of trying to build discrete groups. There are, of course, many other reasons one cares about arithmetic groups that have nothing to do with hyperbolic manifolds, and, well, that's not for us to care about today, at least. So let's look at an example. Or again, alpha is a root of x squared minus 2. Okay. And we'll take the quadratic form, Q. It'll have matrix with an alpha and then 1s. I'm going to make a minus alpha just so it matches up in the order of the lemma. That's fine. Okay. And so we can embed this one way, and we get minus root 2, 1, 1. And we embed it the other way, get root 2, 1, 1. Okay. And so in the language we were talking about before, it says signature n comma 1. Okay, so this is n, n plus 1 by n plus 1. Okay. This is a positive definite form. It has signature n plus 1 comma 0, if you want to put it that way. This is a positive definite form. Okay. So what's going on here is we can look at the set G in Q adjoint alpha such that transpose G equals Q. Okay, this I'll just call as this is just an abstract group. Okay, so I'm thinking about this as just an abstract field. And then we can map this into GLM plus 1 R cross GL m plus 1 R by taking our two different roots. Okay, and then this form now becomes equivalent over the real numbers to the standard quadratic form of signature n1. And this one becomes equivalent to just the standard old quadratic form. So we see that the image lives in ON1 cross ON plus 1, the orthogonal group. Okay. And of course, the beauty here is that this is compact. So, so we see that we end up with a set of G. How about GL? Right, that should be matrices, sorry. So this is just my, oh, that color's not so good. It's just O sub K. Alpha. So the things that are integral that preserve my form. Oops, oh, boy. Okay. And so this is what motivates an admissible form. So I'm not gonna give the full, I don't want this to be too painful. But the point is, so we've produced, so Q gives us a discrete subgroup. Isometries HN. Okay. And it doesn't naturally, let's say you really want to use the standard quadratic form to define the hyperboloid. Well, we didn't start with it. That's okay. There's a change of basis that gives it to you. So this motivates admissibility. So I'll give the general definition, but it's not going to hurt you too badly, I promise. So K will be a number field. And Q will be a quadratic form. On K to the n plus 1, just as an abstract vector space. Okay? Just like I wrote this down in coordinates on just an abstract field with this root. We'll let G, fancy G, either fancy or ugly depending on your aesthetics, I guess. We'll just take the abstract matrices that preserve this form. All right. And actually, maybe I'm going to call this G of K, just for find out why later, but you don't really need to care. And then so we get embedding this group inside a product of GL n plus 1 R, the R cross C to the S. Right. Trying to think about how exactly I want to state this. So the first thing we're going to assume, I guess, I'll just say that we're going to assume S equals 0. So R, K is what's called totally real. So this is part one of the definition of admissible. It's actually a consequence of the definition, but I want to try to ease you into this if you've never been punished by this before. So 2, we have the signature of Q is N1 at 1 real embedding. And n plus 1, 0 at the other, and it could be, it could be the negative of a positive definite matrix. Either one, doesn't matter. Okay. So those are the two. This gives you admissible. And the point here. Sorry? Sorry, I can't hear you. Yeah, so what part don't you understand, please? All of it?
It's written out like signature of Q in n, 1.
Oh, is. Oh, that's enough? Oh, that's great. Yeah, so we're really mimicking the first example where you have one root where you get something that's going to give us a hyperboloid model, and then the rest of them all look like this. That's the point. So then what we get is, I'm going to call it G of OK. GLM plus 1. OK. This goes inside of O(n)(1) cross and all the rest of the factors are compact. So the whole point.
So when conditions 1 and 2 will be called the member field K?
No. So it's going to be. So I'll be more precise in a second. Yeah. Sorry, I'm trying to ease into it, and I'm probably sounding like I'm just not defining it well. Yeah, so this is, I'll leave that. So the pair K and Q is admissible if 1 and 2 hold. Which implies that the things that are integral become discrete. Okay? So admissibility, what's the whole point? What's the key point? Is designed so that exercise 4 produces a discrete subgroup of not just that product, but O(n)(1). Okay? So that's the real idea here, is that the integral automorphisms of this quadratic form, you have all these ways of embedding them in Rn. If you make sure the first one gives you an O(n)(1), that's going to act on hyperbolic space. All the rest of them give you compact groups, and the projection of that action will remain a discrete action. That's the whole idea. That's the whole point. Okay? And now hopefully you've at least seen a little bit of why I went through this whole mess of saying, well, you could take any quadratic form and blah, 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 blah. Because as you vary this process by taking different number fields and different roots, you necessarily get different quadratic forms. And those give you different models of hyperbolic space. And if you really want to understand the geometric invariance of the manifolds that come out of this, you want to work in the model that comes from the form you picked. And I see at least 2 people nodding, which warms my heart, which means I haven't totally lost everybody. But OK, so that was maybe best laid plans, but that's the whole point. So this is exactly where I want to be. So the theorem, nope. I don't know why I put that there. Bad chalk. The case we're discussing, this actually kind of makes me upset. People just say this is a theorem of Borel and Harish-Chandra. This case, and it's the one you most often see in talks, this actually goes back to Hermite in about 1909 or something. But other things I say will be actually due to Borel and Harish-Chandra. So this is an n dash, and this, I forgot which is which. I'm actually going to say Borel and. My arm's starting to get too tired to be precise. But yeah, there's a long history of this problem, and in fact, Borel and Harish-Chandra's most critical contribution is actually in the second part of this theorem. Suppose KQ is admissible, then the image of this G OK and O and 1 is a lattice. Okay. So it says the quotient Hn by the action has finite volume. Okay. That was our original motivating question, was to show that there were finite volume. Well, we wanted manifolds, okay? So we've produced a discrete action. We've said that the quotient by that discrete action has finite volume. But to be the fundamental group, you also need it to be discrete and free. Right? So we haven't talked about freeness of the action. Yeah. So we need there to be no elements of finite order in this. And so I'll state this. We can maybe talk about it more, but I'm low on time now. So maybe we'll circle back to this. This is called Selberg's lemma. It's actually not necessarily attributed to Selberg. I was just very precise about saying Hermite gets written out of this story all the time, and now I'm writing out, say, Malsev and others. But this was known to Malsev around the same time. There is finite index subgroup this G. Okay. Acting freely on Hn. So you get manifolds. And Borel and Harish-Chandra question is compact if and only if there exists a non-zero vector. This is not how they state it in the paper. So that it's a null vector for the form. Okay? So if you can represent 0, sorry? Oh, yeah. yeah, of course. Yeah, thank you. Okay. So again, if we're interested in compact manifolds of constant curvature, we want this not to happen. And as I was sort of mumbling before, this is, in full generality of all arithmetic groups, this is the main contribution of the Borel-Harish-Chandra paper. They proved that you could apply these old methods of Hermite in broader generality than was known before. It's an important part of the paper, don't get me wrong. But the proof of this aspect is important. So if we went back to this, alpha squared equals 2, and we go back to this form, we have an embedding where this becomes positive definite. Right? This is positive definite. So it never represents 0. Okay? So the thing that we get out of this, we get compact manifolds. And so this method was the first node method to produce compact manifolds of constant curvature -1 for all dimensions. Riemann surface theory sort of goes way back. And so I want to give another. Okay, so now let's just take the standard quadratic form, if you want. Or you can take, oops. All right, and so this is just the set of G. And now I'm taking SLN Z plus 1. Preserve this form, okay? And so here we're taking the pair, the rational numbers, comma, the standard form. Okay, this is admissible. Maybe this is part 0, is understanding why this fits the definition. Part 1 of the exercise is to show that SL2Z shares a common finite index subgroup. So many of you who have done hyperbolic geometry have done Mobius transformations acting on the hyperbolic plane, and you're like, these quadratic forms are killing me. So let's bring it home a little. For this one, yeah, I'm going to continue. It's still admissible for higher ed. I'm okay. 3's going to come up soon too. And so how do you get from one model to the other? This hints towards something called the adjoint representation, which to give precise invariance for these arithmetic manifolds, you need to breathe those words, but I think we've been punished pretty hard today, so I'm going to try to be so SL2R acts on traceless matrices. by conjugation. And so you can take the basis. Take 0, 1, 0, 0. Z is going to be 0, 0, 1, 0. So you can look at, so this is a basis, and then so, but the point is it actually lives inside of and so this part of the exercise is to show that the quadratic form on R3 given by so this is the matrix trace. We have x and y in M3R with trace of x equals trace of y equals 0. The point is to show that this defines a quadratic form. Okay, this is called the adjoint action. If you've never heard that word before, that's fine. But this gives a quadratic form on R3. Trace is invariant under conjugation. So SL2R lands in the isometry group of this form. You want to show its signature 2, 1. In fact, I'll even tell you for this basis, it looks like 2, 0, 0, 0, 0, 1, 0, 1, 0. Maybe I should, I used X and Y for those letters. Let's go call them A and B, just so there's no confusion. Trace of AB. Okay. So this gives you an embedding of SL2R and SL3R, and if you do this carefully enough, you can actually show that SL2Z shares a common finite index subgroup with this group. Okay? This gives us the specific hyperboloid action, and I know I need to finish. I'm going to, I promise. I mean, I could keep going, but I think we're okay. So the challenge is to do the same. SL2Z join I SO31Z. I had a bunch more to say, but maybe I'll just stop. I got as many nods for that as I did for. We're done.